Hello everyone and welcome to this week's lightweight Java game library 3D game tutorial, and this week we're going to be covering 3D mouse picking using raycasting. So what this does is allows you to interact with the 3D world using your mouse cursor, which is essentially a 2D coordinate on your screen. The way that we're going to do this is to project a 3D ray that goes straight out of the mouse cursor through the camera and into the 3D world. And the ray represents everything that is currently under the mouse cursor from the user's perspective. So in this example here, the mouse would be going through this tree here and hitting the terrain behind it, or in this example here, the ray would be going straight between those two trees. So basically in this episode, we're going to be converting the 2D mouse coordinates into a 3D vector that is in the world coordinate system. Once we've calculated that 3D mouse ray, we can do pretty much anything with it, but in this tutorial I'm going to be giving the specific example of using it to drag entities around on the terrain. I'm basing this tutorial off a very nice text tutorial that I found online, and I've linked that tutorial in the description, and I would definitely recommend checking that out either before or after watching this video to really help you understand what's going on. So how are we going to convert that 2D mouse coordinate into a 3D vector in world space? Well, if you remember back to tutorial 8, we actually did pretty much the exact opposite of this. In tutorial 8, we started off with a load of vertices for a cube, and like any model that we use in our game, the vertices were all specified in local coordinates, all relative to the model's origin. But we then wanted to put these models at different places in the 3D world, so we transformed each vertex using a transformation matrix or model matrix so that the vertices were all now specified in world coordinates. So the positions of all the vertices were now in relation to the origin of the world. Then we transformed all of the vertices using a view matrix so that all the vertices were then in relation to the camera's position, and this is called eye space. And finally we used a projection matrix to scale the distant objects to make them look smaller, and in general to make our view more of a frustum shape. OpenGL then carries out perspective division on all of the vertices to convert them all into normalized device space, which puts all of the vertices in terms of the OpenGL coordinate system that we've looked at in the past. And finally, OpenGL converts these positions to 2D pixel coordinates on the screen so that they can be rendered, and this space is called viewport space. So our mouse cursor is currently in viewport space, and we want to convert it into a 3D ray that is in world space. So to do that, we will simply have to do the inverse of all of these conversions, so that we can convert back from viewport space to normalized device space, to this one, to eye space, and finally to world space. And definitely check out that tutorial I mentioned if this is confusing you at all, because it explains it all with some very nice diagrams. So let's get right into the code, and the first thing that we need to do is of course to create a mouse picker class. So what do we need to have in the mouse picker class? So the first thing we need of course is going to be the current ray, because the mouse picker class is going to keep track of the ray coming from the mouse, so that's going to be a 3D vector. Then we need to have the projection and the view matrices, so that we can do some conversions with them, because obviously they're going to be needed in the calculations to convert the 2D coordinate to the ray. And we're also going to need the camera, because we need that to create the view matrix. So let's get the constructor done. This is going to take in the camera and also the projection matrix, and then we'll just set the camera and also the projection matrix, and then for the view matrix we're going to create that using the camera, and we've got a method in the maths class that can do that, maths.createViewMatrix, and that takes in the camera. So now we're going to create a method quickly that's just going to get the current ray so that we can access the ray from other classes in our code. So do that quickly. Then we're also going to need a method that does the conversion. So this is going to be the method where most of the action happens, and it's going to convert the 2D mouse position into the 3D ray. But before we do that, we're going to add an update method that's going to be called every frame, and this is going to firstly update the view matrix by creating a brand new view matrix basically using the camera, and it's then going to update the current mouse ray using that method that we're just about to program, the calculate mouse ray method. So the first thing that we need to know is the 2D screen coordinates of the mouse. Where on the screen is the mouse cursor? And we can find this out very simply by calling mouse.getX and mouse.getY, and we're going to want to have those as floats. Now we've got the position of the mouse in viewport space, so the next step is to convert that to normalized device space, basically converting the coordinates from screen coordinates into the OpenGL coordinate system. So let's now create a method that can convert these mouse coordinates into the OpenGL coordinate system. So that's going to take in the mouse X and Y position, and it's going to return a 2D vector, which is still the mouse X and Y position, but in OpenGL coordinate system. And this is the conversion that we're going to use, and hopefully with a bit of thought you can all see why that is. And then we're just going to return these newly calculated X and Y values, which are now in terms of the OpenGL coordinate system. I should also point out at this point that Lightweight Java Game Library uses a slightly unusual coordinate system for the mouse coordinates, in that it calculates the coordinates from the bottom left of the screen instead of from the top left. So if you're following this tutorial and you're not using Lightweight Java Game Library, then you would probably need to change this last line to return a vector containing X and minus Y. But if you're using Lightweight Java Game Library, which I'm sure pretty much all of you are, then you don't have to change anything. So let's now actually use this method to actually do that conversion. So in the calculate mouse ray method, we can now call the get normalized device coordinates method to actually convert that mouse X and Y into a 2D vector, which is now in the OpenGL coordinate system. So now we're at this point, and we now need to convert to clip space. But because this is a special case, because we want to end up with a 3D direction or ray instead of an actual 3D point, we don't actually have to reverse the perspective division here. All we have to do is to make the Z coordinate -1, because that means pointing into the screen, and that's the direction that we want our ray to be pointing. And we also need to add a W component so that we end up with a 4D vector, so let's do that. So now we need to convert to I space, and to reverse this conversion here, we need to transform our vector by an inverse projection matrix. So let's create a method that can do that for us. So this method is going to convert from clip space to I space. So it's going to take in the 4D coordinates that are the clip space coordinates, and it's going to return the 4D coordinates in I space. The first thing we need is an inverted projection matrix, and that's very easy to do in Lightweight Java Game Library. We just have to call the matrix4f.invert method, and that takes in the matrix we want to invert. And also you could put in another matrix which you want to store the result into, but we don't want to do that, so we put in null. And then we can transform the clip coordinates using that inverted projection matrix by using the matrix4f.transform method, and that will create the 4D I coordinates. But we only care about the X and Y components of this 4D coordinate, because the Z component we're going to set to be pointing into the screen, because that's the direction we want our ray to go, so we set that to -1, and we also add the W component to be 0, and now let's actually call that conversion to convert from clip space to I space. So now we have the ray in terms of I space, but we need to go one step further to convert it to world space. Usually, to get from world space to I space, we transform using a view matrix. So to reverse this conversion, we just need to transform using an inverse view matrix. So last thing we have to do is to create a method to do just that. So this method is going to convert from I coordinates to world coordinates. So it takes in the 4D I coordinates, and it's going to return the 4D world coordinates. So just like in the other method, the first thing we need to do is to inverse the matrix, the view matrix this time. So we'll invert the view matrix, and then we can use that inverted view matrix to transform the I coordinates into world coordinates. So we use the transform method again, and that will give us the 4D coordinates for the ray in world space, which is exactly what we want. We're just going to convert it into a 3D vector because we no longer need it to be a 4D vector. So do that, put in the X, Y, and Z components, and we're also just going to normalize the ray because obviously it's just a direction and we want it to be a unit vector. And then just return that ray, and let's call that method so that we can actually calculate the world ray here. So call the two world chords, put in the I coordinates, and we're pretty much done there. So now we can return the world ray. So there we go, we've calculated the projected ray's direction based on the mouse cursor's position on the screen. So let's get this all set up and working quickly. So in the master renderer, we need to have a method to get the projection matrix so that we can use it to create a mouse picker. So create a quick getter method somewhere in here, and then in the main game loop you can create a new mouse picker using the camera and the projection matrix from the master renderer. Then we just need to remember to update it every frame, which we can do by calling picker.update, and make sure to do this after the camera has moved. So now everything is set up, we can get the ray that the mouse is casting, and for now we're just going to print it out to the console so that we can see if it's all working. So let's run the game, and hopefully you'll be seeing a lot of numbers being printed and hopefully no exceptions. And the easiest way to see if it's working is to move the camera right above the player and to put the mouse in the middle of the screen. And if everything is working, then the mouse ray should obviously be pointing in the -y direction, so check if that is happening. So now that you've got this projected ray, you can do pretty much anything with it. You can use it to find out what point on the terrain the user is clicking on, you could find out which entities it intersects with, and you could highlight those entities so that when you mouse over an entity it gets highlighted. You could use it to aim projectile attacks. The possibilities are basically endless. The tutorial that I linked in the description shows a way of calculating ray intersections with spheres, so you could surround all of your entities in bounding spheres and then find out which entity the mouse cursor is over by testing for ray intersections with those bounding spheres. There are a million different things that you could do with this, so I'll leave it up to you to decide what you want to use it for. But I'm going to give you a very quick example of how you could use it to calculate the intersection point of the ray and the terrain. So in the description you'll find a link to an updated mouse picker class which you can download, and then you can just copy and paste it all into your mouse picker class. It's pretty much identical to the code that we wrote, apart from the fact that I've added a few new methods to help find the intersection of the ray with the terrain. You'll also see that the constructor now takes in the terrain, and if you have multiple terrains in your world, then you'll have to make it take in the grid of terrains, and you'll also notice that this class now holds the current 3D point where the ray intersects with the terrain. In the update method, I've added this code here that does a binary search each frame to find the point on the ray that intersects with the terrain, and there are a load of methods down at the bottom that carry out this search. Also, if you're using multiple terrains, then you need to update this method here so that it returns the current terrain for these world X and world Z coordinates, the same way you would have done it for the player's collision detection. It should hopefully just be 3 lines of code looking something like this. I'll just give you a brief explanation of how this works now. So basically every frame it tries to find the intersection point of the ray with the terrain, somewhere between its starting point at the camera and within a certain range. A range which is determined here in the code. It attempts to find the intersection point using a binary search, so it first checks the middle point of the ray and finds out if this point is above or below the terrain. If the point is below the terrain, then the intersection must be in this half of the ray, but if the point is above the terrain, then the intersection must be in this half. So we take the half of the ray that the intersection is in, and then we repeat the process. Check the middle point of the ray, see that it's under the terrain, and so the intersection must be in this part, and then repeat again. Check the middle point is above the terrain, so the intersection is somewhere in here. And this repeats for a number of times determined by this count here, and once it's finished repeating the process for all of those times, it just returns the midpoint of the leftover ray section, which by that time will be very small and it will give you a pretty accurate position for the intersection. Unfortunately, this method isn't without its problems though, because if you have a particularly hilly terrain, then in some cases the intersection could be missed, but in general it works pretty well, especially if your camera is at a fairly high angle. But this is just something that I came up with very quickly, and I'm sure that you guys can come up with your own algorithms. So just to get it all working, you need to give the constructor your terrain or terrains in the main game loop, and then in the while loop you can get the point on the terrain that the mouse cursor is currently pointing to. And if this isn't null, then you can use it to position an entity in the world. So you can see here that I've used it to position a lamp entity and also a light with a bit of a Y offset. And if I run that, you can see that it all works very nicely with the mouse dragging the lamp around on the terrain. So that is it for this week. Don't forget to check out yesterday's devlog video if you haven't already. I was showing off the new magic attacks this week, and a link to that video is on the screen now. Do stay in touch via any of my social media pages, links are in the description below. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a fantastic week, and I will see you all next time.